Hello everyone, my name is Fabienne Salimi, Director of ADEB Academy and co-author of ADEB Applications. In this video, we demonstrate the result of PhD project entitled Intelligent and Multivariable Process Monitoring for HAZOP 4.0. This PhD project is performed by Mrs. Reyhane Mokhtarnameh under supervision of Dr. Ali Akbar Safavi from Shiraz University and Dr. Professor Leonard Erbas from Dresden University. ADEB Academy had honor to contribute to supervision of this PhD project as an industrial partner. Graphical user interfaces and OPC connection of this digital twin have been realized by Mr. Hossein Taghipour. Other vision for interoperability between PSM and OTS has been implemented in this PhD research. This approach is explained in the other book entitled A System Approach to Managing the Complexities of Process Industry. We believe that digital transformation and roadmap to Industry 4 can be achieved only if the fundamentals of system thinking, system engineering, and complexity management are well understood and implemented throughout all management systems. HAZOP is a design review and shall be in compliance with the risk assessment model of ISO 31000. Establishing context is the first step of this risk assessment model. A context may be simple, complicated, or complex. Applying the simple method for the complex context could result to the mediocre or misleading analysis and risk reduction measures. Objective of this research is to consider the complexity in the risk model of ISO 31000. In any risk assessment, complexity can be associated with the context, risk analysis, and risk reduction measures. For HAZOP, complexity should be considered for the node selection, HAZOP scenarios, and evaluation of the process safeguards. This research provides the practical methods to consider the complexity for the node selection and consequence analysis of the complex HAZOP scenarios using the Multivariate Dynamic Simulation. This dynamic simulation can be used for a holistic evaluation of the process safeguards too. Ideally, the process safeguards should be assessed by a dedicated control HAZOP or CHAZOP for short. This will be the subject of our future researches. Now let's see how can we assess and manage the complexity of the HAZOP nodes. A proper node selection is crucial to perform an effective HAZOP. Traditionally, HAZOP nodes are determined intuitively and based on the engineering judgment. In this research, we have been inspired by the Cynefin framework, which is a simple and qualitative decision-making tool. Therefore, it can perfectly match the qualitative nature of HAZOP. Cynefin framework asserts that any given context is fallen in one of the 5 categories that we see on this image. The simple contexts are well known and can be managed by applying the best practices. The complicated contexts need to be understood through the analysis and good practices. The complex contexts are characterized by their unpredictable dynamic behavior and should be understood by the trial and error. The chaotic contexts should face the unknowns, and therefore they should be managed by trial and error too. The disorder contexts are vague and unclear, so before any attempt to manage them, their complexity level should be reduced. This slide shows how we apply the Cynefin complexity categories to the HAZOP nodes. In general, only simple, complicated, and complex categories are applicable to the HAZOP nodes. Chaotic cases are reserved for the novel processes which process licensors or conceptual designers may need to consider. Disorder cases may be observed with the HAZOP of aging plants which were subjected to many changes without applying a proper management of change procedure. In these cases, the first step is to put order in the historical data and information about these changes. Complexity of the HAZOP nodes can be characterized by the number of equipment or unit operations in the node, diversity of the equipment or unit operations in the node, connectivity of the equipment or unit operations in the node, and finally, nonlinearity of the unit operations or process fluid transformation. Each of these characteristics are ranked as low, medium, and high. To calculate the complexity level of HAZOP nodes, we have allocated a weight to the complexity characteristics and the intensity numbers to the rankings. These values are estimated based on our engineering judgment. The ranking criteria for the 4 complexity characteristics are calibrated based on the engineering judgment and domain knowledge for the styrene polymerization, chain reactions, and processes. Calibration table may be customized for a given process. We hope this approach and the complexity calibration table can be standardized in the future. Nodes should be optimized to be as simple as possible. Complexity level of nodes can be optimized with a few trial and error using other HAZOP monitor. Now let's see how it works on SharePoint. Operating management system is in place to assure the operational excellence of the organization. Process Safety Management System, or PSM for short, is one of the operational excellence sub-management systems. Both CCPS and Energy Institute PSM framework consist of 20 elements. There are a few differences between the order and breakdown of the PSM elements of CCPS and Energy Institute. Element 6 of Energy Institute, or 7 of the CCPS PSM framework, is dedicated to the hazard identification and risk assessment, also known as HERA. HAZIT is the first HERA activity. ISO 1776 provides a comprehensive checklist for the credible hazards in a typical oil and gas facility. The project-specific hazards, which cannot be found in the checklist, can be easily added. For example, we have added a new category for chemicals and added styrene, polystyrene, ethylbenzene, and TBC to this list. Water is considered as non-hazardous material, but if a closed water section is exposed to a sudden and large heat load, water explosion can occur. This is a credible hazard in the refineries and petrochemical plants. Therefore, we added water to the list of project-specific chemicals. Very often, the HERA activities remained unconnected and scattered. Other PSM monitor is designed to create the integration or interoperability between the HERA activities from HAZIT, Desktop Safety Review, PNID Review, HAZOP, LOPA, SEAL, etc. The actions of these activities can be tracked and followed up in an overall all-in-one application. We will demonstrate this concept in the further slides. Now let's concentrate on the HAZOP methodology that we have applied in this research. Node selection and optimization is the first step of HAZOP. Case study is the HAZOP of complex styrene polymerization process. I click on this link, which takes me to the list of HAZOP nodes. First of all, I can quickly see the HAZOP markup, description, boundaries, and supporting documents. Then I would like to check the complexity level of this node. I choose the complexity content type, which let me rank the 4 characteristics of complexity. I rank with the help of the calibration table nodes, which are found under each complexity characteristic section. The complexity level of node is calculated automatically. Objective is to reduce the complexity level of node to the lowest possible level. For example, if we rank the first polymerization reaction node, we reach to the complexity level of Cl3. The dominant factor is the nonlinearity of the polymerization reaction. We may decide to reduce the boundaries of this node to reactor only to achieve a lower complexity level of Cl2. Because of the complex nature of polymerization chain reaction, we cannot reduce the complexity level of this node to Cl1. Now I click on this link to get access to the HAZOP brainstorming worksheet. If I click on the node and complexity, a pop-up will be appeared and I can navigate between the HAZOP node markup and complexity assessment. Then I click on each hazard number to remember the hazard associated with the process and utility fluids in this node. HAZOP brainstorming is also available. Finally, I click on the HAZOP scenario number to explore the discussions about the causes, consequences, and safeguard of this case. The complexity type of consequences could be ranked as CT0, CT1, CT2, and CT3. CT0 means that there is no complexity with this case. CT1 means that the amplitude and duration of deviation should be scrutinized. CT2 means that the multiple causes or multiple failures are credible and their consequences should be scrutinized. CT3 means that the consequences of this cause can be propagated and lead to the domino effects. In the complexity description field, the HAZOP team captures the details of complexities and uncertainties which need to be scrutinized with the univariate or multivariate dynamic simulation. This dynamic simulation will be performed outside HAZOP brainstorming session by the expert in the dynamic simulation. The result of dynamic simulation will be reported in the HAZOP action sheets and then will be captured in this content type to be available online. LOPA can be integrated as a content type to the HAZOP worksheet too. The risk reduction from the independent layers of protection will be captured during the brainstorming session and the LOPA calculation will be performed automatically. The failure rates can be captured manually or through the databases that we have created per your HAZOP on SharePoint. With the same approach, alarm management, seal studies, and the other relevant studies can be integrated as the content type to the HAZOP worksheets. By doing so, we create an all-in-one HERA application which will be available at any time and anywhere to the personnel. Now I click on this link to screen the complex HAZOP scenarios which are ranked as CT1, CT2, and CT3. The results of the univariate and multivariate dynamic simulation can be visualized quickly on the digital twin of the process by clicking on this link. This page is a web-based SCADA HMI interface, and therefore the HAZOP team or operator can react with the simulation and observe the results of the cases that they are testing. For example, they can open close valves or start-stop pump and observe the behavior of whole process immediately. The dynamic simulation results could be discussed in a complementary HAZOP brainstorming session, as well as in the further studies such as alarm and seal assessment. During operating phase, this digital twin, which encompasses all the EPC rationale, can be used for the troubleshooting and operator training. As my final word, I would like to inform you that this method is published in a paper entitled Application of Multivariable Process Monitoring Technique to HAZOP Studies of Complex Processes. Now I hand over the presentation to Mrs. Reyhane Mokhtarnameh to explain in detail the results of her multivariate dynamic simulation to improve the HAZOP study of an existing Styrene polymerization plant.
Hello everyone, my name is Reyhane Mokhtarnameh and I performed this research as a double-degree PhD program of Shiraz University and TU Dresden. Arab Academy has co-supervised this research as the industrial partner of Shiraz University. In the previous part of this demo, Dr. Salimi has explained the methodology proposed by this research to implement complexity assessment and management in the HAZOP procedure. Now I'm going to present the results of our approach to adapt the multivariable process monitoring techniques for the HAZOP studies. The method is applied to an existing 25-year-old polystyrene polymerization plant. My presentation covers a brief description of the styrene polymerization process. Then I demonstrate how univariate dynamic simulation can be applied to the consequence analysis of the complicated HAZOP scenarios. Finally, in multivariable process monitoring context, first our innovative approach to identify critical process conditions using multivariable process monitoring technique, or shortly MPM, is discussed. Then it is demonstrated how the results of MPM can be easily used to interpret the consequences of complex HAZOP scenarios. Finally, holistic evaluation of the process safeguards for some given HAZOP scenarios is investigated. The styrene polymerization process can be divided into three nodes of feed and recycle system, first polymerization reactor and second polymerization reactor. In node 1, TBC is used as a styrene stabilizer in the storage tank and then it is disappeared. Then the fresh feed styrene is mixed with the feed from the recycled drum consisting of unreacted monomers and solvent recycled from the second reactor output. Solvent is also added to the reactor to control the content viscosity and reactor's temperature whenever its concentration decreases in the reactors. In node 2, the process of the first reactor polymerization is completed by 35%. Reactor is protected against the runaway reaction by the inherently safer design of condenser E2. In node 3, the process of the second reactor polymerization is completed by 60%. Reactor is protected against the runaway reaction by the inherently safer design of condenser E3. Process safeguarding strategies are also demonstrated in this figure. For instance, process safeguarding strategy for overpressure in the first reactor is discussed in the next slide. The inherently safer design for runaway reaction cannot protect the polymerization reactor against all the overpressure scenarios. The process safeguarding strategies against overpressure cases are as follows. The first protection layer is basic process control system. In this process, cascade TIC and PIC is used to control reactor temperature and pressure by manipulating pressure valve 110 on the line between the condenser E2 and ejector J1. The next is primary protection, which includes pressure switch high and pressure switch high. Pressure switch high alerts operators by alarm, closes nitrogen gas valve, and opens pressure valve 110 completely. Pressure switch high automatically alerts operator and starts ejector J2 and create a stronger vacuum. This will cause loss of valuable and hazardous styrene and ethyl benzene vapors to atmosphere. Finally, the secondary protection is a pressure safety element 110, which opens and relieves the reactor content to a cyclone, which sends the vapor to safe location and collect the wasted polymer gel in the portable reservoir. Overpressure occurs due to different causes. Complexity of each cause is ranked during the HAZOP brainstorming session, and therefore the consequences of these cases can be scrutinized with the multivariable process monitoring. Let's have a look again at the screening of complex HAZOP scenarios identified during the HAZOP brainstorming session of the first polymerization reactor. The complexity categories as defined by Cynefin framework can also be applied to the complexity type or shortlist CT. For simple HAZOP scenarios, the checklist and standards provide the required guidance, and the HAZOP team should just verify if they are applied to the given HAZOP case. For example, according to API 14J, if the pressure difference delta P across a check valve is greater than 1000 psi, a double and diverse check valve shall be applied. These cases are ranked as CT0. CT1, CT2, CT3 HAZOP scenarios are considered as complicated cases if a dedicated analysis is needed to understand the dynamic behavior of the process and the known correlations. The Univariate Dynamic Simulation is necessary and sufficient to scrutinize these HAZOP cases. CT1, CT2, CT3 HAZOP scenarios are considered as complex cases if a dedicated analysis is needed to understand the dynamic behavior of the process, but the correlations are not known. The multivariable process monitoring is applied to provide a holistic understanding of the dynamic behavior of the process. HAZOP is a systematic heuristic approach which aims at identifying the probability hazards quickly. Using experience to learn and improve is the formal definition of heuristic. This approach can be effective only when we are looking at one failure at a time, which are the simple HAZOP cases, and the responsive process to them are well known and can be found in the relevant standards, guidance, and checklists. Subjectivity is another weakness of HAZOP studies. The quality and resolution of HAZOP studies is highly dependent on the knowledge and experience of the HAZOP team. A given case can be assessed very differently by two different HAZOP teams. The subjectivity of engineering judgment of HAZOP team can be improved by providing the relevant checklist, standards, lesson learned, etc. to them. Analysis of complicated and complex HAZOP scenarios are commonly ignored to keep HAZOP brainstorming sessions simple and focused. Actually, heuristic approach fails for the complicated and complex HAZOP scenarios, which need a dedicated analysis to understand the responsive process to cases such as multiple failures or domino effect. These cases should be scrutinized by the appropriate dynamic simulation to provide an objective basis for the HAZOP brainstorming. Please note that domino effect in the context of HAZOP means that the consequence of a node is propagated to other nodes. Now let's see how simulation analysis works in the Ignition platform. Welcome to the Hope Styrene Polymerization Plant PSM 4.0 platform. By clicking Process Area, different sections of process plant is shown in the next page, including styrene storage area, polymerization area, drying area, and packaging area. In this demo, we are focused on the polymerization unit. In this page, process description and the simple schematic for the case study process is given. As in this demo, we are focused on the HAZOP analysis of polymerization unit. By clicking the HEWA and HAZOP LOPA seal, you can see the three nodes mentioned in the previous slides: feed and recycle system, first polymerization reactor, and second polymerization reactor. Then selecting each node, P&IDs associated with each node can be seen, which are important inputs of HAZOP analysis. We can navigate between different process deviation for each node. Let me consider high temperature deviation in the node first polymerization reactor. There are different causes for this deviation. For instance, by clicking Cause 1, a pop-up menu is opened including Worksheet, Univariate Simulation, and Multivariate Simulation. In the Worksheet menu, a description of each deviation cause is given. Cause 1 is input feed temperature increase due to more heating in the preheater E1. Besides, there is a link to give you an access to the HAZOP worksheet. In the Univariate Simulation tab, simulation trends of different process variables can be seen. Consequences of different amplitudes of feed temperature can be investigated. I increase feed temperature to 80 centigrade from the normal value of 70 centigrade. Now I give some time to update the simulation trends. As you can see, simulation trends of different process variables are plotted over time. In univariate simulation, effects of each deviation cause on different process variables should be analyzed one by one. As can be seen, reactor temperature and pressure are firstly increased and then will return to the normal operating condition value due to the correct action of controller. In this scenario, condenser output temperature is increased and reactor level remains unchanged. This quantitative analysis can be performed for all process deviations. In other words, this platform could be an important part of a cyber-physical system development and analysis. Here, the user can interact with simulator during design phase or training mode and also connect to the real physical system via SCADA platforms. Multivariable Process Monitoring for HAZOP study, a novelty of this research. First, I would like to discuss why we believe multivariable process monitoring is beneficial for HAZOP analysis. As process systems are getting more complex, consequences of complex HAZOP scenarios are much difficult to predict or even are non-predictable through a heuristic assessment. Besides, HAZOP deviation scenarios are generally due to multiple causes, and as a result, the change of each deviation cause has a different effect on the process conditions. Therefore, to perform a thorough HAZOP analysis, all possible complex scenarios are needed to be analyzed. Although such analysis is essential, it is very time and effort consuming. As another fact, the common univariate analysis of complex processes, where in reality many process variables interact, may be insufficient and not completely present multivariable process behavior. Besides, holistic evaluation of the effectiveness of process safeguards with univariate simulation is close to impossible. This research suggests systematic variations of all possible causes with different amplitudes as well as their credible combinations, and use related simulation results within the MPM framework. Multivariable process monitoring is an effective method for monitoring of process key variables for abnormality detection and diagnosis. This monitoring technique can also help alarm management in the process industries. The novelty of this research are as follows. First, MPM is applied to improve the understanding of the complex HAZOP scenarios by a holistic interpretation of the process dynamic behavior. Second, besides of the common normal operating region layer shown in many process monitoring analyses, and since the focus of HAZOP study is more on critical process conditions, a new multivariable process monitoring layer is invoked to identify the critical conditions of process variations further than the normal operations. In general, in this research, a combined PCA-SVDD monitoring algorithm consists of two layers of decision boundaries is proposed. The first layer is based on normal operating conditions, and the second layer is based on a safe operating condition of plant. Now let's see how MPM analysis is performed in the ignition platform. This figure shows the basic view of the proposed monitoring method. In this research, this analysis is performed for the second node. In this node, 4 critical variables are considered as monitoring variables. To define the normal operating condition, or shortly NOC, for this study, we collected the input and output data from the real operating polystyrene in the industry for the normal operating conditions. When we are in the design stage, this data can be collected from the simulator. To initiate the monitoring method, simulation sample data under normal operating conditions are fed into the PCA to determine the most effective principal components, which lead to dimension reduction and better analyzing components. In this case, the dimension of process data is reduced to 2 through PCA from the original 4 dimensions. The normal data points are inputted to the SVDD algorithm to best fit a contour to these data. This way, the NOC contour is obtained, which is used for detection of abnormal process conditions. The collected safe operating condition, or shortly SOC data, generated by process simulator are also projected into the 2D principal component subspace. The SVDD algorithm is then used to obtain the SOC contour, which is used to detect critical process conditions. Direction of different process deviations, for instance, high and low reactor pressure, high and low reactor temperature, high and low reactor level, and high and low condenser output temperature, are also somehow conceptually highlighted in different colors to provide a better interpretation of the monitoring results and make the analysis readily understandable for the HAZOP team. This easily shows how each failure can affect the process conditions. It is worthy to mention that the NOC and SOC boundaries remain unchanged unless the process behavior change. In the following slides, the figures are zoomed in and out for a better view. Besides, in some cases, if the numbers of monitoring variables are high, one may choose to have the projected principal component to 2 or even 3 with accepting less approximation quality, or we may subdivide the main monitoring picture to several two-dimensional pictures. Now, I would like to highlight the added values of the MPM method for HAZOP analysis. MPM framework helps better understanding of correlations between process variables. The proposed monitoring algorithm provides a valuable tool for easy interpretation of process dynamic behaviors. Multivariate analysis of process conditions provides a more accurate analysis. Utilizing this technique, deviation scenarios that force process condition to approach its critical limit are identified. The sensitivity and effects of each deviation cause on the target process variables can be easily obtained from monitoring results. Safety response time for deviation scenarios can be easily recorded. To optimize process safety measures, the correlation between process variables should be well understood. Adequacy of process safety measures can be verified through such a multivariate analysis with a holistic concept in some reasonable effort. The first scenario is reactor high temperature due to more feed temperature. This deviation is examined considering two different amplitudes of the deviation cause. You can see monitoring results for 20% input feed temperature increase with blue circles. Direction of process data movement shows temperature increase in both the first reactor and condenser output temperature. However, the system is in the safe region. Monitoring results for 40% increase shows that the process data moves further away from the normal region and gets closer to the critical limit. The performance of cascade temperature controller is also depicted in this figure with yellow squares. As can be seen from the monitoring results, the reactor temperature increase is compensated by the controller. In contrast, the load of condenser is increased as process data approach the region that shows the condenser output temperature increase. Overall, the effect of input feed temperature increase on the reactor temperature is not significant even for large failure amplitudes, and flawless function of cascade temperature controller guarantees the quality of product. The second scenario is reactor high pressure due to more injection of nitrogen gas to the reactor. Monitoring results for 5% nitrogen gas flow rate increase in the first reactor shows a sudden pressure increase and consequently temperature increase in the reactor. 9% nitrogen gas flow rate increase results in process data exceeding the safe critical limit in 15 minutes. In this failure scenario, obviously the sensitivity of process condition to even small amplitudes of nitrogen gas flow rate is much larger compared with the more feed temperature increase in the reactor. Besides, the safety response time is much smaller. This means that appropriate process safety measures are required to react to such events in a timely manner. The adequacy of control systems and other process safety measures are illustrated in this figure. Finally, the effect of solvent flow rate on the polymerization is scrutinized in this slide. The main consequence of higher solvent flow rate to the reactor with no control system in place is level increase leading to overflow if it is not controlled in time. The first protection layer, level controller LIC110, is activated, which reduces the styrene monomer feed flow rate to keep the reactor level constant. This results in lower reaction rate, in temperature decrease in the reactor that leads to less vaporization rate, and consequently, the condenser output temperature decreases. In this case, safety response time is much larger compared to when LIC is not active. To compensate for temperature decrease in the reactor, the cascade TIC-PIC controller is also activated, and the monitoring results is plotted with yellow squares. As can be seen, even with control systems, process condition is still moving away from the normal region. Although reactor level and temperature are under control, the condenser output temperature is reduced, and finally, after about 6 hours, the reactor temperature is sharply decreased, leading to plant shutdown. This is due to domino effect of this deviation cause on the reactor's conditions. This shows that available safety measures are not sufficient to prevent this operability issue, and some recommendations are required. The real plant shutdowns records also demonstrate that this plant has experienced several shutdowns at early years of operation due to wrong solvent makeup. Now let's see how MPM analysis works in the ignition platform for a given scenario. As mentioned previously, for each deviation cause, there is a pop-up menu which gives access to HAZOP worksheet, Univariate Simulation, and Multivariate Simulation. By clicking Multivariate tab and then make it full screen, the MPM analysis can be performed. In this demo, the deviation cause more input feed temperature is simulated for 20% increase. Real-time data points from MATLAB software, where the mathematical model is developed, are transformed to the ignition through OPC connection. As can be seen, for this case the process condition is in the safe operating region. For other deviation amplitudes, the consequences can be easily observed. Simultaneously, the real-time univariate simulation can be also observed in its related tab. This presentation summarized the first part of this research. The second part will try to implement artificial intelligence to HAZOP studies. Thanks for your kind attention, and I would like to hand over the presentation to Dr. Salimi to close this demo.
At this stage of demo, I would like to thank Reyhane for her rigorous research during the last 3 years and this nice presentation. Please also be informed that we will apply this method for other complex processes and will publish our finding in a book entitled A New Approach to HAZOP of Complex Chemical Processes. Publication of this book is scheduled for 2022, and we will be grateful to hearing your feedback and suggestions to optimize this method. Thanks for your kind attention, and have a safe and reliable operation.